Good morning. In the last class, we were discussing regarding cyclic redundancy check codes, that is CRC codes. We discussed way in which CRC code will going to be generated and how they are helpful in detection of errors. So, today's class we are going to discuss regarding few examples on CRC. First, by taking one example, we will discuss regarding how CRC code will going to be generated. That is, that process we call it as encoding process. So, I will take say 1 0 0 1 as a data or data word. I am calling it as data word. This is my data word. Then I will going to use 1 0 1 1 as a divisor. This is what I discussed in the last class. This divisor is a thing which is agreed by both sender and the receiver. So, that means divisor is known to both sender and receiver. So, as it was told to you in the procedure, to start with, what we are going to do is first step in generating the code word is our data word will going to be appended with few number of bits. The number of bits what we will go to append to the data word, it entirely depends on number of bits in the divisor. In this case, there are 4 bits in the divisor. We will going to append 3 bits to a data word. These are my appended bits. So, I appended 3 bits to my data word, and what I will do is I will do the procedure of dividing this appended data word. Now, to start with, anyway, the division what we will going to perform over here is of modulo 2 arithmetic, modulo 2 division. To start with, I look at say the MSB bit of dividend, then based on that I will select my quotient. Anyway, it is a binary division. To start with, it is 1. Now, my data word will going to be say divided by this 1 0 1 1. So, here we are performing a only XOR operation, not a actual subtraction like in our normal division. So, 1 XOR 1 is 0, 0 XOR 1 is 1, 0 XOR 0 is 0, 1 XOR 1 is 0. These are the things which are left over after performing this part of the division. Then we have to take the next bit, that is the 0. My word will going to be this one. So, anyway, the MSB bit. See, in this whole procedure what we are doing is we are trying to make MSB 0. So, here after performing making a MSB 0 over here, this bit of will be my MSB now. So, looking at this, I will going to decide what should be the quotient. Now, it is 0. So, if it is 0, then it is divisor will go to be 0. So, then I will perform XOR operation of this becomes 1 0 0. Then I will go for the next bit, I will pull the next bit, so that is 0. So, again I will do the same thing. So, looking at MSB, I will decide MSB bit of this dividend, I will decide what should be my quotient, it is 1. So, then again I will perform the XOR operation, then again say I will take the next 0, this is 0, 0 1 1 0. So, I will be left out with the remainder 1 1 0 0. The modulo 2 binary division what we have performed over here is same as that of our normal division process. We use for say there we use decimal numbers. However, addition and subtraction in this case are same. We use a XOR operation to do both for addition as well as subtraction. We are using a XOR operations. The process of division remains same as that of our decimal division. So here we are performing the division same as that what we do in our decimal division process. So in each step what we are doing, we are copy of the divisor is XORed with the 4 bits of dividend. So at every steps the copy will going to be XORed. One thing you keep it in mind, the result of XOR operation at every step will going to give us a 3 bits, because every time my MSB will be equal to 0. You see in all the steps, so I am making these MSB bits 0. So in the end what I will going to be left out after performing that XOR operation, I will going to be left out with 3 bits. So we are continuing this process till we end up with some remainder. One thing you remember, if the leftmost bit, yes, if it is 0, in that case, so I will going to use, we need to use all 0 divisor. That is one important point over here. When there are no bits to pull over or pull down, say we will going to stop our division operation. Whatever the thing that is left out, we will going to take it as remainder. So in this case the remainder is of 3 bits. So these reminders we will going to call them as check bits. These are my check bits. So it is R2, R1 and R0. They are, these R2, R1, R0 will now going to replace these zeros. So those things will going to be the one which will be helpful in creating my code word, that is, this is my data word, and earlier I appended a 0 here, which will now going to be replaced by this these reminder bits. Those are 1, 1, 0. So these reminder bits will going to be now appended to my data word. So now this data word will going to become a code word. This will be my code word. This created code word will going to be sent to the receiver. At a receiving side, we are performing, or the receiver will going to perform a check on the received code word to verify whether the received code word is correct or not. Now at a receiving side, when the receiver receives the code word, to begin with I will assume that whatever the code word that is sent by the sender, the same code word is received at the receiver. With this assumption, I will perform the verification of the code first. Thereafter, we will introduce some error in the received code word and we will verify the outcome. So to start with, I will assume that the sent code word itself is received at a receiver. So the sent code word is 1001 and 110. This is what is the sent code word. Okay, we will assume that there are no errors during the transmission. So the same code word is received at the receiver. Now how exactly receiver will come to know this is a correct code word or not? For that, again receiver perform some set of test on this received code word. The test what receiver will do is the same thing what the sender has done on the sending side. So it uses the same divisor to divide this code word. Is it clear? So the thing is that it will now going to divide the code word by using the same divisor that was used at the sending side. So this was a divisor which was used to create this code word, and the same divisor will now going to be used at another entity, that is receiver, and it will now the receiver will going to perform the division operation on the received code word. Okay. To start with, like the procedure remains same, again it is a XOR yeah, I mean modulo 2 binary division. So, again the procedure remains same. To start with, look at this bit and then decide the quotient. It is 1 0, I mean quotient will be 1, it is 1 1, it is 1 0 1 1. This division will going to create this outcome. I will going to be left out with 3 bits. So, I will going to pull the next bit, it is 1 over here, in this case it is 0 1 0 1. Now, looking at this bit, MSB bit of this dividend, we will going to decide the quotient, it is 0 in this case. Now, the process remains same, XOR 1 1 XOR 0, it is 1 0 1 0. Again you pull the next bit, next bit pulled is 1. So, in this case the quotient will going to become 1 1. So, after that this becomes 0 0 0 0. Next I will going to pull 0, since this MSB bit is 0, this quotient is 0. So, after performing this division operation, I will going to be left out with say 3 zeros. My reminder, here we are not interested in the quotient, our interest is in this remainder. So, after performing a division operation on the code word, what it is received. So, in this case none of the bits of the code word got changed during the transmission. So, the same code word is received and we perform the division on the received code word and we are getting the remainder as 0. So, this itself will going to signal us whether the received code word is say correct or not. If the remainder of this division is 0, that is my R2, R1 and R0 bits, if these bits we call them as a syndrome, actually these are my syndromes. Just refer the figure that what we have discussed in the last class. So, these syndromes, if all these syndrome bits, so rather than using a R, I am going to use a notation S, S2, S1, S0. If these my syndromes, if they are 0, I am going to conclude that the received code word is correct. So, there are no errors in the received code word. If S2, S1 and S0, if they are non-zero, that means if this remainder is non-zero, in that case the conclusion is that the received data is say received code word is having some errors. Let us discuss one such example. So, I will going to change one of the bit of this code word to verify. So, what I will do is 0 0 1 and I will change this bit, say this bit I changed. So, it is flipped. So, there in actual code word it is 1, here it is 0. I change one bit and I will perform the test on this bit by using the divisor. So, to start with, so 1 1. So, after performing a XOR, this is 1, this is 0, this MSB is 0, I will pull the next bit. So, quotient is 0 0 0 0 0 0 1 0. So, I will going to pull the next bit, it becomes 1 1 0 1 1, XOR it 1 1 0 0, you pull the next bit, so it becomes 0. So, if it is 0, the quotient is 0 0 0 0, 0 XOR 0 is 0, 1 1 XOR 0 is 1 0. So, I will going to be left out with this remainder, that is 1 1 0. My syndrome is S2, S1 and S0 is 1 1 1 1 1 0, which is non-zero, syndrome. So, this indicates that there is a error in the received code word. So, but this will not show where exactly the error has taken place or in which bit there is an error, it is not possible for it to indicate. So anyway, it is only a error detection code. For that reason, its job is to only indicate whether there is an error in the received data word or not. The better way to understand these cyclic codes and how they can be analyzed is to represent them as a polynomial. Again, this is optional. Already what we have done, or already what we have discussed, same things is applicable to a polynomials also. Or if you express the data word or the code word in terms of polynomial, so the same operation we are going to perform on the polynomial. We will see one such example. I will take one, say, binary pattern, and I will try to represent that in a polynomial form. So let us take one example where my polynomial will my binary pattern is 1 0 0 double 0 and it is 1 1. Just for understanding reason, I have taken one pattern. So this is my LSB and this is my MSB bit. So I will try to represent this in the polynomial form. So this is x raised to 0 and the quotient will going to become 1. Here the quotient of the terms of polynomials, either it will be 0 or 1. Where all 0 comes, that particular term will going to be a 0. Where all 1 comes, only that term will going to be a part of our polynomial. It is 1 into x0. In this case, x0 is all every time it is 1. So actually it is a 1. Then plus, look at the second bit, it is in the x raised to 1 position and its value is 1. Next, x square and the quotient is 0. The next is x cube into 0. X square, this is x cube, then this is x raised to 4 into 0, then x raised to 5 into 0, last is x raised to 6. So that time it is 1. So the polynomial I will rewrite over here because of the space problem. So I will rewrite this whole polynomial. X raised to 6 term is there with quotient 1, and next x raised to 5 term is 0 because the quotient is 0. X raised to 4 is also 0. X raised to 3 is also 0. X raised to 2 is also 0. But whereas x raised to 1 will going to be there, that is x, the quotient is 1, and next x raised to 0 term is there because the quotient is 1, so that is 1. So the my polynomial representation of this bit pattern is this one, that is x raised to 6, x and 1. So only these 3 terms are present in this whole bit pattern. So if it get represented in the polynomial, it will be like this: x raised to 6 plus x plus 1. As you know, the degree of the polynomial is the highest degree, that I mean highest power in the polynomial. That will be the degree of the polynomial. Say in this case, the degree is, say, is 6. Now I will take a previous example itself. I will try to represent that in the form of polynomial, and I will perform that CRC division using polynomials. So the previous case, my code word which I generated was 1001, and for this data word, before converting it to a code word, we appended a 3 zeros. If I represent this in the polynomial form, it becomes x raised to 6 plus x cube, only 2 terms are there, fine. Then my divisor was 1011 in the previous example. So if I represent this in the form polynomial form, it becomes x cube plus x plus 1, because x square term is 0, because the quotient of x x square is 0. Okay, this will be my divisor, this will be my, I hope it is clear, this will be my divisor and this will be my code. Okay, still I will not going to call it as a code. So, data word after appending a zeros, this is what is the polynomial it will going to generate. So, let us perform the division operation on this polynomial. Let us start the division operation. So, it is not x6, it is x cube, divisor is x cube plus x plus 1 and this is x raised to 6 plus x cube. Okay, to start with, so first I will going to multiply this divisor by x cube. So, after multiplying that with the x cube, this becomes x raised to 6 plus this becomes x raised to 4 plus this becomes x cube. So, in this case this term and this term get cancelled, this and this get cancels, I will going to be only left out with x raised to 4. Then next look at this x raised to 4. So, this becomes x, this will going to gives rise to x raised to 4, my quotient is x. So, plus x square, x into x is x square plus 1 into x is x, this becomes, these two get cancels, this is x square plus x, this is what is my remainder. So, that is actually 1 1 0. So, after appending that to the data word, that my data word was x raised to 6 plus x cube, to this if I append this, it becomes plus x square plus x. This is what is the polynomial of the code word. So, this itself will going to be sent to the receiver, and this is my data word and this is my code word. I hope you understood. Same way at a receiving side, I mean this is my data word and this is my reminder or syndrome which is appended to this. So, together it is code word. Okay. So, similar operation will going to be performed on the receiving side to verify the received code word is correct or not. So, you can perform that also by using a polynomial. So, I leave it to you for say like what exactly happens at the receiving side, convert that to a polynomial. So, I have already discussed two examples of verifying this received code word. So, you try to convert both the examples in the form of polynomial and perform the polynomial division and verify. The advantages of these cyclic codes, just now what we discussed, is that the cyclic codes have very good performance in detecting single bit errors, double bit errors and odd number of errors and burst errors. They can easily be implemented using a hardware and a software. They are bit faster, I mean they are fast when implemented in hardware. So, many a times we implement this CRC generation and verification by, we do it by using a hardware to increase the speed. So, apart from this, I would like to add few more things regarding this CRC. So, one more important point regarding this CRC is that, so the divisor what we use to generate these code words, these divisors are, say, normally they will be are of the type, they will be a standard one. Okay. So, when we express them, when we express these divisors in a standard form, we call them as a standard polynomials. So, I will just list out few standard polynomials over here. So, which will be very widely used in different protocols, which are very widely used in different protocols. So, I will just list out few of them over here. These polynomials which I will going to list out, they will be widely used in different protocols for CRC generation. That is, first I will start with CRC8, cyclic redundancy check 8, CRC 8 code word is, so here 8 indicates the highest degree of the polynomial, that is x raised to 8 plus x square plus x plus 1. If I convert this into a bit pattern, so this becomes say 1 0 0 0 0 0 triple 1. I hope it's clear. So 1 2. Yes, so this is what is its equivalent binary representation. This is the standard polynomial. So the same, if you convert it into a bit pattern, it looks like this. Next is CRC 10. So that is x raised to 10 plus x raised to 9, so plus x raised to 5 plus x raised to 4 plus x square plus 1. This is one more standard polynomial. So I'll just list out say few. Then CRC 16. So this is very important from the point of view of say your network lab. Okay, that is x raised to 16 plus x raised to 12 plus x raised to 5 plus 1. So that is, you convert that into a bit form and you will come to know how exactly it will going to be, like what kind of a bit pattern it will going to generate. So I'll write it over here. So 1 3 zeros, 1, then 0 0, then again 2 zeros, another 2 zeros, 1, then 0 0 0 0 1. Let us see, 1 2 3. Yes, correct. So this is my CRC 16. So these are the few standard polynomials which are widely used by different protocols for generation of CRC. And in the next class, I will going to discuss regarding hardware implementation of this CRC. That too by taking the previous example itself I will going to use to create its hardware circuit, and then we will also going to discuss regarding a checksum in the next class. So in this class we discussed example on CRC and some standard CRCs. Apart from that, how to represent these CRCs in the form of polynomial. Okay, so thank you very much. If you had any doubts, please feel free to ask the questions. So post your comments in YouTube. Yes, it will be very helpful for us to improve our say next video.